Computer Architecture, MIPS Assembly, Functions, Part 3. I plan to present this in 2 parts, but I will make some extra comments on this, so I will talk another 10 minutes about functions. So let me close this one. First of all, I want to talk to you a little bit about the connection between assembly and higher programming languages like C or other imperative programming languages, because now we understand how the variables work. We have a program, that part of the program that is called main, and there all the variables are global and they're on the heap, and we already know where this heap is. Let me show you this. This data segment, this is what we call the heap. This is where you store your, let's say, static variables, the one that you declare at the time when you write your program. You declare your variables in main, and the moment the program starts, these are placed in memory. This is called heap, this kind of memory. But if you call a function, the variables cannot be at the heap, because if the function starts calling another function, or even worse, if the function starts calling itself, if it places them on a static place in the heap, it will start overwriting itself. Therefore, they must be on the stack, and they must be growing the stack every time you have a function call, and every time the function ends, they are removed from the stack and the memory is liberated. So now we have 2 types of memory, and we can see them here. This is the data segment, this is the heap memory, and we have the stack pointer. This is dynamic. All the variables that are here are temporarily, and the moment they are no longer needed, they are removed from the stack. So we have heap and we have stack. And in the previous video I have shown to you how to use the stack, how to place our registers on the stack, especially the T registers from T0 to T7, and here T8, T9. Don't ask me why they're separated like this. And the S registers from S0 to S7. I explained to you how you have to, how the calling program, for instance main, has to take care of the T registers to place them on the stack if needed, and the callee, that means the function that is being called, that has to take care of the S registers. So now we have main, variables are global and are in the heap. Functions, variables are local and are on the stack. Global variables are static, they have a known address at the time of compilation, and space for them is reserved by the compiler. Local variables are dynamic, their addresses are determined at runtime. Space for them is reserved to them by assembly program. They disappear from memory when the function finishes. That is to say, of course, if the assembly program is correct. Now let's go back here to the file that we have written. You can see here the main program, and what it was doing, it was having a loop from 0 to 10, and then calling 10 times, calling with that iteration value, let's call it I. In fact, it is T0, as you can see, and then call a function that calculates the square and then prints this square. And I want to now to talk to you about how to communicate with a function. You should never communicate through the S and T registers. They are just local, let's call them variables, registers for calculations. When you want to pass information to a function, you have to do this through the A0 and A3, the arguments. So if you remember in C programming, when you declare a function, you always had between brackets, you place the arguments. This is what goes into the function. And if you want to return something, well, most functions or a lot of functions are void, so they don't have to return anything. But often a function returns maybe an error code or something like this, an integer. Then you can place them on V0 and V1. So you have 2 return value registers and 4 argument registers. So never use them for local calculations in principle, and never use these for local calculations. The local calculations are done with the T registers and S registers. Now I want to finish here with explaining to you what now if a function calls a function. Let me first explain to you again how this went. When we want to call a function, we do the jump and link, my function. This is my function that will be jumped to. Jump and link saves the current address of the current instruction plus 4, so that is the instruction to that is following, that is this one in this case, load word. It is saving that one in the return address register here. And if the function finishes, when it says jump on register, it takes the return address and puts that in the program counter. So it's doing nothing more. Jump on register here, return address is doing nothing more than copying return address to the program counter. But what now if this function itself is also calling a function? You will have a problem. Let me show you what will be the problem. Imagine that I do the calculation of calculating the square is done here in function, but I want another function that is my function, let's call it my function 2, and what it is going to do, this is the one that's going to print it. So let me copy paste here because I'm rather lazy. Argument, it is A0, well you have to pass through the argument, the integer to print. Output returns nothing, void, meaning it prints something on the screen but it doesn't print, it doesn't return anything to the calling program. And then this one here can now, this my function for printing, it can now call actually my new function. So to just jump and link my function 2. And then when it comes back from there, it can go, it will jump back to this one. So I do here jump on register RA. So what happens? Here we have a function call, it saves this address on RA, and then it will execute this thing, stack attack attack. It will get here a function call to my function. So it saves this address of this instruction on RA. So we lose the original value. Then it executes this and this and this. Here it will jump on register. It will put the program counter equal to this function here, to this instruction following, and then it will do jump on register RA. What is the value of RA now? That is the value of this instruction itself. That is not what we wanted. We wanted that it now jumps to here. So how do we do this? Brilliant solution. We have replace RA on the stack. How do we do this? Remember here, add to the stack, add immediate stack pointer -4, and then what do we want to place there? Store word, return address, 0 offset to the stack pointer. And then now this one return address is saved somewhere. When it comes back, what can it do? It has to, of course, load word, return address, 0 offset from the stack pointer, and then we can add, don't forget, don't be lazy, don't forget this one, otherwise you will mess up the stack, you will get stack overflow things like this. And now we have replaced I placed it all in place. We have to do it before the function call. So it should be here, and this one x v. Now we have, before we call function 2, it will place the return address on the stack. It will go to function 2. When it comes back, it will retrieve the return address from the stack, and it can do jump on register RA and jump back now to this one. This, let's see if we did everything well. This has an argument A0 int to print. Okay, in A0 we already have the value we want to print. That's nice, so we don't have to actually do any calculation here. We just have to put 1 into V0 and make a system call, and that is print the number. That is now the square. Let's see if it works. I seldomly write programs that compile well. Well, I'm amazed. And let's then run it, and you see 0, 1, 4, 9, 16, 25, so that is the square numbers. I hope that you get what I'm trying to convey here. The idea is, the things I'm saying here is that now we understand all the registers that are here. 0 is the one that has 0 value always, it's hardware coded 0. AT is for the compiler, so don't mess with that. V0, V1 are return values for your functions. A 0 to A3 is arguments for your functions. T0 to T7 are the registers that you can use at your leisure. And don't forget to save them on the stack. And this is being done for the T is done by the calling program, and for the S is done by the called program. And then the other ones is for the kernel, as you remember. I will not talk about this one, but you will now understand the return address is important, and the stack pointer, this is important, and of course the program counter. I hope you understand how this works, and see you in the next lecture.